According to the 2020 National Electrical Code, the connection to the water service and building steel should be sized at 12% of the total area of the incoming service conductors. Let's examine how to calculate this for two different electrical services. For service number 1, which is a 4000 amp, 120/208 volts, 3-phase, 4-wire service supplied through 10 sets of 4/600 kc mil conductors and 10 4-inch Schedule 80 polyvinyl chloride conduits underground. A calculation is as follows. First, determine the total area of the incoming service conductors. This is calculated by multiplying the number of sets of conductors, the number of conductors per set, and the cross-sectional area of each conductor. In this case, that's 10 sets times 4 conductors per set times 600 kc mil. The conversion factor to convert kc mil to square inches is approximately 0.1506 square inches per kc mil. Therefore, the total area of incoming service conductors equals 10 times 4 times 600 kc mil multiplied by 0.1506 square inches per kc mil, which equals 361.44 square inches. Next, calculate the connection to the water service and building steel, which is 12% of the total area of incoming service conductors. This is 12% times 361.44 square inches, which equals 43.37 square inches. Now determine the approximate size of the bare copper conductors that correspond to this area. 43.37 square inches corresponds to approximately 4/0 American wire gauge bare copper conductors. Moving on to service number 2, which is a 5000 amp 277/480 volts, 3-phase, 4-wire service supplied through 12 sets of 4/600 kc mil conductors and 12 4-inch Schedule 80 polyvinyl chloride conduits underground. The calculation is similar. Firstly, calculate the total area of incoming service conductors. This is 12 sets times 4 conductors per set times 600 kc mil, multiplied by 0.1506 square inches per kc mil, which equals 433.73 square inches. Secondly, calculate the connection to water service and building steel, which is 12% of the total area of incoming service conductors. This is 12% times 433.73 square inches, which equals 52.5 square inches. This corresponds to approximately 5/4/0 American wire gauge bare copper conductors. Therefore, to summarize, the connection to the water service and building steel for both service number 1 and service number 2 should be sized at 12% of the total area of the incoming service conductors, which corresponds to approximately 4 or 5/4/0 American wire gauge bare copper conductors, respectively. It is crucial to consult the latest edition of the National Electrical Code and local regulations to ensure compliance with all applicable requirements. The NEC provides specific tables and guidelines for conductor sizing and grounding electrode conductor requirements. Always verify these calculations with a qualified electrical engineer or inspector to ensure the safety and proper functioning of the electrical system. In electrical systems, grounding and bonding are critical for safety and proper operation. Grounding provides a path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers to trip and clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same electrical potential, reducing the risk of electric shock. The water service pipe and building steel are commonly used as grounding electrodes. The connection to these electrodes must be properly sized to handle the potential fault current. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. In general, larger service entrance conductors require larger grounding electrode conductors. The 12% rule is a simplified way to determine the minimum size of the connection to the water service and building steel. However, it is essential to consult the NEC tables for the specific requirements in each situation. The grounding electrode conductor must be connected to the water service pipe within 5 feet of its entrance to the building. The connection must be made with a listed fitting or clamp. The grounding electrode conductor must also be connected to the building steel. The connection must be made to a structural steel member that is grounded. If the building steel is not accessible, the grounding electrode conductor can be connected to a metal frame of the building. It is important to note that the grounding electrode conductor must be continuous from the service equipment to the grounding electrode. Splices are not allowed in the grounding electrode conductor. If the grounding electrode conductor is damaged, it must be replaced with a new conductor of the same size. In addition to the grounding electrode conductor, a bonding jumper must be installed between the service equipment and the neutral conductor. The bonding jumper ensures that the neutral conductor and the service equipment are at the same electrical potential. The size of the bonding jumper is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the bonding jumper based on the size of the service entrance conductors. It is important to note that the bonding jumper must be installed in a manner that provides a low impedance path for fault current. The bonding jumper must be connected to the service equipment and a neutral conductor with listed fittings or clamps. In some cases, additional grounding electrodes may be required. For example, if the water service pipe is not metallic, an additional grounding electrode, such as a ground rod or a ground plate, must be installed. The additional grounding electrode must be located as close as possible to the service equipment. The grounding electrode conductor for the additional grounding electrode must be sized according to the NEC tables. It is essential to inspect the grounding and bonding system regularly to ensure that it is in good condition. The connections to the grounding electrodes must be tight and free of corrosion. The grounding electrode conductors and bonding jumpers must be protected from physical damage. If any problems are found with the grounding and bonding system, they must be corrected immediately. Proper grounding and bonding are essential for the safety and proper operation of electrical systems. By following the NEC requirements and best practices, you can ensure that your electrical system is properly grounded and bonded. In summary, when sizing the connection to water service and building steel, firstly, determine the total area of the incoming service conductors. Secondly, calculate 12% of that area. Thirdly, select the appropriate size and number of bare copper conductors to meet or exceed that area. And fourthly, always consult the latest edition of the NEC and local regulations. Always verify these calculations with a qualified electrical engineer or inspector to ensure the safety and proper functioning of the electrical system. Remember to always prioritize safety when working with electrical systems. Always to energize circuits before working on them and use appropriate personal protective equipment. If you are not comfortable working with electrical systems, consult a qualified electrician. Understanding the National Electrical Code requirements for grounding and bonding is critical for ensuring the safety and reliability of electrical installations. These calculations, while seemingly straightforward, are based on fundamental principles that protect people and property from electrical hazards. The code is updated regularly to reflect new technologies and best practices, so staying current with the latest edition is essential for electrical professionals. For example, ground fault protection is another vital aspect of electrical safety. Ground fault circuit interrupters, or GFCIs, are designed to detect small imbalances in current that indicate a ground fault and quickly disconnect the power, preventing electric shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas where there is a higher risk of contact with water. Surge protection is another important consideration, especially for sensitive electronic equipment. Surge protective devices, or SPDs, are designed to protect against voltage surges caused by lightning strikes or other electrical disturbances. SPD can be installed at the service entrance or at individual equipment locations. Proper installation and maintenance of SPD can significantly extend the lifespan of electronic equipment and prevent costly damage. Electrical inspections are a critical part of ensuring compliance with the NEC and local regulations. Electrical inspectors are trained to identify potential hazards and ensure that electrical installations are safe and code compliant. Regular electrical inspections can help prevent fires, electric shocks, and other electrical accidents. Working with a qualified and licensed electrician is always recommended for any electrical work. Licensed electricians have the training, experience, and knowledge to perform electrical work safely and correctly. They are also familiar with the NEC and local regulations. Attempting to perform electrical work without the proper training and experience can be dangerous and may violate local codes. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical engineer or inspector before making any decisions about electrical installations. The NEC is a complex and comprehensive document that requires careful study and interpretation. There are many nuances and exceptions to the general rules, so it is essential to have a thorough understanding of the code before applying it to a specific situation. Electrical safety is everyone's responsibility. By following the NEC requirements, using qualified professionals, and staying informed about electrical safety practices, we can all help prevent electrical accidents and ensure the safety of our homes and workplaces. Remember, electricity is a powerful force that must be treated with respect. Always prioritize safety and consult with qualified professionals when working with electrical systems. Let's delve deeper into the practical aspects of grounding and bonding, specifically concerning large electrical services like the 4000 amp and 5000 amp examples we discussed. These large services often supply power to entire buildings or large industrial facilities, making the integrity of the grounding and bonding system paramount. Firstly, let's revisit the concept of the grounding electrode system. The grounding electrode system comprises all available electrodes, such as the metal water pipe, building steel, concrete encased electrode, also known as a U for ground, and ground rods or ground rings. The NEC mandates that all these electrodes, if present, must be bonded together to form a single, effective grounding electrode system. This interconnection ensures that all parts of the system are at the same potential, minimizing voltage differences that could pose a shock hazard. Secondly, consider the importance of low impedance. A low impedance path to ground is crucial for quickly clearing ground faults. The lower the impedance, the higher the fault current will be, which allows overcurrent protection devices to operate faster and more effectively. This is why the NEC specifies minimum conductor sizes for grounding electrode conductors and bonding jumpers. Larger conductors offer lower impedance. Thirdly, let's talk about the supplemental electrode. While the metal water pipe is typically the primary grounding electrode, it must always be supplemented by an additional electrode, such as a ground rod, ground ring, or concrete encased electrode. This requirement is in place because water pipes can be susceptible to corrosion or may be replaced with non-metallic pipes in the future, which would compromise the grounding system. Fourthly, consider the location of connections. The connection to the metal water pipe must be made within the first 5 feet of its entry into the building, and it must be accessible. This allows for easy inspection and maintenance of the connection. The connection to building steel should be made to a main structural member, ensuring a reliable and permanent connection. Fifthly, let's address the common misconception about grounding and lightning protection. While a properly installed grounding system helps to protect against electrical faults, it does not provide adequate protection against direct lightning strikes. Lightning protection systems are specialized systems designed to divert lightning current safely to ground, and they should be installed separately from the electrical grounding system. Sixthly, consider the use of exothermic welding. Exothermic welding, also known as CAD welding, is a process that creates a permanent molecular bond between conductors. This type of connection is often used for grounding electrode conductors and ground rings because it provides a highly reliable, low-resistance connection that is resistant to corrosion. Seventhly, let's discuss the importance of documentation. A detailed record of the grounding and bonding system should be maintained, including the location of all grounding electrodes, the size and type of grounding electrode conductors and bonding jumpers, and the results of any grounding impedance tests. This documentation is essential for future maintenance and troubleshooting. Eighthly, consider the specific requirements for hospitals and healthcare facilities. These facilities have stringent grounding requirements due to the sensitive electronic equipment used in patient care. The NEC Article 517 provides detailed requirements for grounding and bonding in healthcare facilities. Ninthly, let's talk about the impact of harmonics. Harmonic currents can cause overheating of neutral conductors and transformers, and they can also interfere with the operation of sensitive electronic equipment. Proper grounding and bonding can help to mitigate the effects of harmonics by providing a low impedance path for harmonic currents to flow back to the source. And tenthly, consider the importance of ongoing maintenance. The grounding and bonding system should be inspected regularly to ensure that all connections are tight and free of corrosion. Grounding impedance tests should be performed periodically to verify the effectiveness of the grounding system. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. By paying close attention to these details, electrical professionals can ensure that large electrical services are properly grounded and bonded, providing a safe and reliable electrical system for the building and its occupants. These considerations highlight the complexity and importance of grounding and bonding in modern electrical systems.